Hello, everyone. Welcome to our lecture, to our talk. My name is Stanimir. This is my colleague Patrick. And we're going to talk about our journey from going from custom in-house cluster to AWS, from Python to Scala, from Scikit-learn to Spark, and let's say from CherryPy to Play, Scala Play. Couple of words about us. We are both have background in computer science and have PhD in some application of machine learning. At Zalando, we are both switching between machine learning and engineering, so machine learning engineer sums it up pretty well. Zalando is our employee, is Europe's leading fashion platform. Here are some quite impressive numbers for a company which started 2008 as a simple, small online shop selling shoes in Germany. Now it operates in 15 countries, has 3 fulfillment centers, nearly 20 million active customers, 3 billion euro revenue, 160 million visits per month on the web page, and currently around 1,300 employees in technology only. I encourage you to visit tech.zalando.com, which is our technology blog, and you can find quite a nice blog posts about techniques and technologies that we use. A very recent one, for example, is about using RNNs, deep learning, for ad tech industry. And Zalando technology is living a culture which we call radical agility. So if you're curious, go to radicalagility.org. Now this is how the Zalando web shop looks like. And a brief history of Zalando technology started in 2008 with a simple PHP and MySQL shop. 2 years later, adopted more and more technologies, more stable and more up-to-date technologies, and this is continuously growing. Around 2015, we introduced functional programming in Scala and Clojure, and probably our move to Spark and Scala is kind of a part of this effort. Number of employees goes beyond 1,300, and Zalando technology is hiring, so if you're interested, go and check out the job opportunities. So what we do at Zalando, we are part of a team which is called Payment Analytics and is concerned with finding and preventing fraud of incoming orders. So we employ different techniques and technologies. We kind of have to know about Spark, Scala, R, SQL, AWS, continuous integration, Jenkins, all that stuff, plumbing stuff with shell scripts and so on. Our products, so to say, are models which we train on historical data, but we don't end there. We take responsibility from end to end, so we put our products also to production. So if you think about, fraud detection and prevention boils down, in our case, to modeling the fraud probability, to assigning a fraud probability to each order that we are queried about. So one way you can deal with fraud probabilities to sit and start writing rules. Like if some customer hasn't paid his orders for the last 1 year, he'd probably also not paid the current one. But if you do this more and more and more, it kind of starts getting nasty. So modeling fraud probabilities beyond just writing some business rules. So our take on it is to use machine learning. We use historical data to train models, and these models then are used to predict fraud probability for each incoming order. This has the advantage that it's free from bias. It's totally data-driven. It's free from human biases and human prejudices also. So let me give you an overview of our current setup for prediction and runtime. We have the Zalando shop where people click around and eventually come to the checkout. And at this time, the shop sends a query to our service, asking what the fraud probability for this for the order would be. The query looks like some JSON query, and from this JSON query, we first extract some features. This might be very simple static features, but also might be some more involved dynamic features which you need a model for, and you get some kind of a feature vector out of it. Parts of this feature vector might be empty because some data is missing. So in the next step, you need to again having some model to find a way to impute these missing values to fill the gaps, so to say. And eventually, with the complete data vector, you feed it into the final model, which gives you the estimation of the fraud probability, which is then taken by the shop for some business decision, like whether this order is allowed to be placed with a specific payment option and things like this. Okay, so how do these models come into place? So first we have our data sources. We don't have a single data source. We have different data sources. Some of the data comes from logs. Some of the data comes from Exasol. Who knows about Exasol? Well, quite a few guys. Exasol is a column-based in-memory database, which is supposed to be very fast. Hello, funny. So this is where the data comes from. We have also a configuration for each of the models, right? What kind of features you take, what kind of imputer you plug in, what kind of a predictor you use. Like, is it a linear model or some non-linear model? And the numbers are crunched by on a cluster managed by Slurm. Once the models are prepared, they are written to a worm drive, worm being write once, read many, in order to ensure the integrity of the models over time. And this is where they get into the service, which is queried, as I showed on the previous slide. So when the shop, queried it. So you might imagine that this, like having different models for different countries and for different customer segments, so on, results in quite a lot of models. So we want to make sure that we are scalable. Why is scalability a big concern? Because the numbers, as you might see here, for 2014, 2015 are growing, and we expect this to be amplified by the fact that Zalando evolves from being just a shop in the past to a fashion platform which connects all the stakeholders on the fashion market, starting from producers, going through advertising agencies and logistic services and whatnot, and ending at online retailers and actually also offline retailers. So scalability is a major concern. And this is how our current setup hurts us. So these are the most, or maybe the four top points which hurt us. Let me start at the bottom. So we are crunching numbers on an in-house cluster, which is not only available to us, but also we are sharing it with other teams. So you cannot be always sure that the cluster is available to you at the moment that you expect it to be. So this kind of slows us because we cannot respond very quickly to requests from the business, basically. So back to the top. The problem with cluster also is that it can be very powerful, but still you can't go over the boundaries of a single machine because we use Python. So for a single model, we can, the parallelization that we can reach is to learn different models on different machines, but you cannot go beyond the boundary of a single machine for a single model. So we cannot basically horizontally scale our learning training process. Another thing is that actually a lot of data scientists love Python for its concise syntax and for not having to, write all these nasty types for each variable and so on. So it allows you to very quickly bootstrap your idea and come up with rapidly with a prototype. But if you don't put extra work and really have a very, very sane and comprehensive testing, you end up with having troubles with maintenance when you deploy to production. So the last point is that we kind of find out that our design decision in the past was not so optimal. We were basically fetching freshly data every time from our data sources for every time we learned. So coupling, we were coupling data acquisition and learning. And it turned out that we had a bottleneck with Exasol, which is kind of fast, but if it's shared with another department, it comes at its boundaries in our case. So this is what gave us a lot of pain in the past, and we sat back and designed and decided that we have to rethink our concepts and redesign our systems, and that's where I hand over to Patrick to guide you.
Hi. So my name is Patrick. I'm running you through the second part of the presentation, which is basically about the redesign. So Stanio mentioned that we had a lot of pain points when we tried to scale out our Python solution, and that was about the same time when the word about Spark did the round. So we sat together and we thought about solutions, and we did not only came up with Spark, but we also changed to Scala, and we moved on AWS at the same time. So quite a change. And the reasons for this are like Spark, I think as every one of you knows, is it promises that we can scale out, so we just throw more hardware on our learning problem, and Spark will figure out for us how to do that. The other thing is, for us coming from Scikit-learn, we were used to having very mature libraries for machine learning. So we didn't want to do something where we had to implement logistic regression or something else on ourselves. So we another reason for going to Spark was MLlib. So mostly it had already most of the algorithms we use. And then we still had the decision, okay, Scala, Spark supported at the time already Python, and we were, okay, should we do Spark and then use Python? But then we soon figured out that all the APIs that we're interested in, that they're like a half a year later only in Python. So for us it means going to JVM, learning Scala, but what we also knew with our computer science backgrounds, it's like you get type safety, which is really good for our team, which is about 8 or 9 people now, because if you have such a big code base, it was always a problem when you onboard people. They cannot really fully understand your code because they don't know what type is inside the variable. So this got a lot better with Scala, I would say. And one other thing what we get for free then is real multi-threading. So I will show you some experiment result later on, but since, as Daniel mentioned, we have end-to-end responsibility, and one of the issues we faced that we have a production system which was running in Python. So we had a lot of problems when there were too many requests simultaneously coming in, and the problem is that Python does not real kernel-based multi-threading. Okay, at the same time, Zalando decided to move to AWS, and so we took this opportunity to set up our new system completely on AWS, and of course, this gives us a lot of benefits like this unlimited computing power, which is almost unlimited, and cheap data storage. So I think most of you are aware of this. Just want to show again our old solution on the left. So we have this Exasol, and we have the in-house cluster, which is called Slurm. So what we did in the past for learning, we just extracted all the data from this Exasol database, did the learning, and then saved the model at this warm drive. And what we now do, I mean, that's what Spark basically does. It loads the data from HDFS, which is in our case S3. Then we do a lot of computation of learning the model, and then we save it back to S3. Okay, so this is one of the things which gave us Scala, and this is how you configure your model. So on the left side, I think you cannot really read it, but that's intended. We have, if you want to have a Python model, like you want to have not hard-coded everything in the code. So what we have, or what I think most of you have, is a configuration file where you say, for this country, I want this features, and I want this regularization, I want this training data, I want this test data frame. And then you put this stuff in a configuration, which is loaded at learning time, and your model is learned. So in the Python world, this was just a text file, which is loaded, and then it's deployed on the Slurm, you run it, and if you have a typo in it, you somehow see, okay, that's not good, like Python was not able to see, there's no compile time, so you were not able to see if something wrong. What we did now in the Scala world, we just put all our features in case classes, so it's now really Scala code, which gives us, on the one hand, compile time safety, even for our configuration, and on the other hand, it's very easy to, as you see here, you can extend things like scorers, which are like multi-level features in our case. So the definition of a model is very concise because you can reuse a lot of code. So what we also built then is, since we learn the models in Scala and Spark and save it to S3, we also want to have a runtime which uses Spark as well, because what you probably not want to do is you want to run, load your model in a different language than you saved it to. So we also were faced with this issue, build a runtime that does online prediction, because we have to do it for every order. So we have something like 1.5 second time to return a fraud probability. So we thought about, okay, we are not like backend engineers or something, but then we looked in the Play framework, which is Scala based, or I think it's also in other languages, but there's one in Scala. And it was very easy for us to build a REST interface to load the models from S3 into memory at startup, and then to have real multi-threading also on the JVM. And one other thing which we got from moving to AWS, we are now in control of our data, because I think most of you know S3 is a really not expensive storage solution. So all these data sources we had, Exasol was one of them, then some databases. In the old setup, we could not afford to store them somewhere else, so we basically extracted it offline and then did the learning. But what we can do now is we can save everything beforehand in S3. So what Zalando does basically is every team has an AWS account. Every team is end-to-end responsible of what happens in there. But as S3 is very cheap, you can just also have your own data. So we have a job that does it for us, and then we are not bottlenecked by any of these resources, because we can go to slots in the night or somewhere at one when these systems are not really overloaded. So this is the advantage which brought us AWS. So now there's a comparison part where I try to more or less see what the old solution did and what we can do now much better. So this may be a little bit surprising, because we could actually reduce the lines of code. And I think it's mainly attributed because we had a lot of learnings during rebuilding the stuff, but also we had a much more code reusability in Scala than in Python. And as I mentioned before, the config is much conciser, as we saw before. And then the learning time. So this should not be like a hard comparison, but it's of course interesting for us. The old solution was like on one cluster, and Python based, and now this new solution, which we run on AWS with one master and 5 workers, was distributed. There is of course more computational power, but a lot of communication. So if you have algorithms like logistic regression, they are very communication intensive. So all the weight vectors, they have to be aggregated at the master, and then you do a lot of cross-validation. So you can scale out easily, but it's not unlimited. You always have to buy in some communication. But we did an experiment where we just put the same amount of data in the old solution and run the same algorithms. And with this setup, the learning time dropped by a factor of 2. So this was kind of surprising. We could get much faster with Spark because we had the feeling always that, okay, if you can get something in one machine, this will be always faster as in a distributed setup, which is actually also here not the case. So this already paid off. And then one of the other reasons which Stanimir mentioned is the data size. So Zalando wants to get even bigger and they want to have more orders. So for us it means much more things that we couldn't put in the learning engine. And as you usually know, if you have more data, typically you get better models. So what we did, we tried out, okay, what happens if we put 10 times the data points in our Spark AWS setup? So we never could execute that on Python because we were just limited in memory. Now we could really do that. And what we ended is we, as expected, we have much better accuracy in the end. Okay, so this is the thing which I mentioned before. It's about the prediction time, and we did some experiments with a Python prediction engine, which we had before, and our new one, which I just showed. And you have to read it from top down, and what you see on the y-axis is the number of requests we sent to the prediction engine, and on the x-axis you see the execution time. So if we start here, we just sent one concurrent request. So actually we are sending sequential requests. We are waiting for the results, and in red you see the answer time for Python, and blue you see the answering time for Scala. So you see one request, not a problem for Python, it's as fast as in Scala. But if we now increase the number of requests, so here we're at 10 and here we are 20, you see there's a gap here. So, and this is also what we observed in the online system we had. So if there's rush hour at Zalando, so Sunday night and everybody orders a lot of stuff, then we are really slow. And now with our new solution, this is much better. So this brings me to the lessons learned. So when we started, it was about 1 year ago, then we were thinking about all these pain points and we are thinking about Spark AWS, and the good thing is, as I think the experiments showed, that almost everything worked out, so all these pain points are gone. So even the scaling works as expected, so we could put much more in data into our learning, so it was not only a big refactoring, but we also get improved accuracy. And we saw a speed up not only in learning, but also in execution if we go to Scala instead of Python for the back-end module. The bad thing, of course, for us as more data scientific people, we all somehow did Java in the past, but never Scala. So we had to learn Scala first thing, which was not so difficult actually when you come from Python. What was really hard though is that debugging in a distributed execution environment is really hard. So a lot of times we face this old problem with distributed execution, that it works locally, but it does not work on the cluster. And at that time we used EMR, and it was sometimes really hard. So you have to go to the logs of some workers, you have to check what's going on different machines, you do heat dumps at different levels. So somehow we mastered it all in the end, but gave us some headaches. And one last thing which also bugged us was the maturity level of MLlib. So at least when we built the stuff, Scikit-learn was much more advanced. So we had some issues where we want to assign weights to different classification classes. I think this was introduced only in Spark 1.6, and it's still not ready for all the algorithms, which you just get out of the box for Scikit-learn, for example. Having said this, I want to thank you and also reference to our tech blog, which you can find behind this QR code here or under this URL, which we wrote about this whole journey. And in this tech blog, you will also find much more about these technical challenges, which I just mentioned. For instance, one other thing we had a hard time with sparse data, so we built a custom condenser to merge them to dense data points, things like that. Check out this blog post if you're interested, and of course we both are around, you can ask us. So thank you.
Thank you.
Just take one of these. Questions? Anyone on that side of the room? Okay, someone, finally. Great.
Okay, so first of all, great talk, thanks. I have a question regarding the transition from Python to Spark. I mean, in the local setup, you don't have to take care of networking issues. You have a limited number of memory, you have a number of CPU cores, but on your cluster with 5 nodes and 1 master, you can tune the driver memory, the executor memory, networking issues, protocols, and also number of CPU slots. And as you mentioned earlier, you train different models for different applications. I assume some models like random forest or SVM demand a different cluster configuration. So how have you dealt with this problem?
We actually currently use more or less the same configuration for all the learning jobs. What differs is, well, the number of executors for some of the more data-intensive jobs, more data-intensive models. But a part of that, and well, also bigger driver nodes for them, because we experienced some memory problems at some time. But a part of that, actually, we haven't played a lot with tuning parameters. That's on our to-do list. We believe we can crunch a bit more out of it, squeeze a bit more out of the setup, but it was actually a secondary concern. It's yet to come.
Did you use any Spark vendor in your configuration?
Sorry?
Did you use any Spark vendor, or was that just basic Spark?
Yeah, we just used plain Spark. So we downloaded the sources and then did everything on our own. So yeah, no vendor involved, just open source.
Hey, thanks for the talk. I don't know if I missed this, but you mentioned that you were using EMR but are not anymore. So what are you using instead?
Yeah, that's right. So we have our own solution. So it's called a Spark appliance, and it's based on EC2 instances. I think it's actually open source, so you should find it on the Zalando open source page. And then it's just a setup where it uses the Spark standalone application master manager, and then you can just configure with Docker, I think, with a Docker file, how many nodes should be spawned up. And you have a CloudFormation stack for AWS, which more or less takes the configuration between all the nodes and things like that. So it's pretty easy, it's pretty convenient, and I think it's much cheaper. Right?
Yeah, the one reason is that it's cheaper, and the other reason is that actually for compliance reasons we needed to use this because of our legal department and all that stuff.
Great, thanks.
There was a question here. I might repeat if you...
Yeah, I can also speak louder. A classic problem in fraud detection is that you have a delay between the moment that you label the case as potentially fraud and the moment where a human has actually gone through the transaction or verifying that this is indeed fraud. And the question is, when and how do you feed back that case into your model, labeled as fraud or not fraud or potentially fraud or not labeled, or how do we deal with this delay? If it takes 1 week to check a potentially fraud case.
It takes, yeah, it might take even, okay, the question is how do we deal with the problem that verifying that something was fraud or not fraud actually takes a week or even longer, and how do we feed this information back to our system? Actually, we don't currently, well, it wasn't possible in the past to retrain our models that often. Now this is another additional value that we get from this switch, that we want to much more often retrain our models. and then it will kind of automatically get into the training data, right? Because you take into account, or we take into account, only data for which we are sure that they were fraud. And we're working also on well, more, algorithms which take into account very sooner what the persons that verify whether it's fraud or not say, but we are not done yet with this.
Okay, guys, I think we need to break for coffee now. Okay, so please show your appreciation for Stanimir and Patrick.
Thank you very much. Thank you very much.